Robots are supposed to be the future, faster than us, stronger than us, smarter than us. And yet, they keep falling over. Embarrassingly, repeatedly, sometimes in slow motion. And it's not because engineers are bad at their jobs, it's because walking, actually walking, is one of the hardest problems in all of engineering. You just don't realize it because you've been doing it since you were 1 year old. Let's fix that. Your body right now is doing something extraordinary. Without you thinking about it, without you trying, without you even caring, your brain is receiving thousands of signals per second from your muscles, your joints, your inner ear, and your eyes. It's processing all of that simultaneously, and it's making hundreds of tiny micro-corrections every single second just to keep you upright. That's not walking. That's controlled falling. Every step you take, you're essentially throwing yourself forward and catching yourself at the last moment. Your body has just gotten so good at it that it feels effortless. Now imagine trying to build that from scratch. In metal, with motors, with code. This is where it gets interesting. The first problem is the center of mass. For a robot to stay upright, its center of mass needs to stay directly above its support base. For humans, that support base shifts with every step, from 2 feet to 1 foot to 2 feet again. The window where you're balanced on one leg is tiny. We handle it automatically. Robots have to calculate it in real time. Early robots solved this by cheating. They moved incredibly slowly, they kept their legs wide apart, and they never let their center of mass leave the safe zone. It worked, but it looked ridiculous. That approach is called static stability. You're always technically balanced, never technically falling. The problem is that real walking isn't static. It's dynamic. Real walking involves momentum, and momentum means risk. This is why early bipedal robots walked like they desperately needed the toilet. Then engineers started thinking differently. Instead of avoiding the fall, what if you just got really good at recovering from it? This is called dynamic balancing, and it changed everything. The idea is simple in theory. Let the robot fall slightly, detect the fall, correct before it becomes a real fall. Repeat forever. In practice, this requires something robots historically didn't have: fast, accurate feedback from the real world. This is where sensors come in. Modern bipedal robots are covered in them. Gyroscopes measure rotational velocity. Is the robot tilting? Accelerometers measure linear acceleration. Is the robot moving unexpectedly? Force sensors in the feet measure exactly how much pressure is hitting the ground and where. And all of that data gets fired into a control system that's running hundreds of times per second. The control system asks one question constantly: what do I need to do right now to not fall? And it adjusts every motor, every joint, every millisecond. But here's what took engineers years to figure out. It's not just about reacting to falling. It's about predicting the ground. When you walk across a messy floor, you don't stop and calculate every step. You glance ahead, build a rough model of the terrain in your head, and your body adapts as you go. Robots need to do the same thing. This is where computer vision and real-time mapping come in. A robot that can see the ground ahead, that can build a map of what's coming, can plan its steps instead of just reacting to them. The difference is enormous. A reactive robot stumbles and recovers. A predictive robot doesn't stumble in the first place. Now, you've probably seen Boston Dynamics videos, Atlas doing backflips, spot dancing, robots that move in ways that genuinely do not look mechanical. What you're watching there isn't just impressive hardware. It's the result of a technique called model predictive control, where the robot is constantly simulating its own next few seconds of movement. It's not just asking, what do I do now? It's asking what's the best sequence of moves for the next half second, and then executing that, and then asking again. It runs that loop so fast it looks like intuition. But it gets even more interesting. Some of the newest robots aren't programmed with movement rules at all. They learn to walk through trial and error, just like a baby does. This is called reinforcement learning. The robot tries something, it falls, it gets a penalty. It tries something slightly different, it falls less, it gets a small reward. Repeat that millions of times in a simulation, and the robot figures out how to walk on its own. Nobody told it how, it discovered it. And when you then transfer that learned behavior into a real physical robot, it just works. That's not programming, that's teaching. We're still not at human-level bipedal movement, not quite. Humans handle unpredictable terrain, sudden shoves, and split-second changes in a way robots still struggle to match. But the gap is closing faster than most people realize. 5 years ago, a robot getting kicked and staying upright was headline news. Today it's a Tuesday. The engineers working on this aren't just building robots that walk. They're solving one of the deepest problems in all of physics and computer science simultaneously. How do you build a machine that exists in the real world, messy, unpredictable, chaotic, and doesn't break? The answer, it turns out, involves a little bit of maths, a lot of sensors, some very clever software, and occasionally, watching a robot fall on its face 10,000 times until it figures it out. That's engineering. And we're just getting started. Subscribe to Assembly Labs now.